All right, today we're going to start chapter 2. We'll try to get only 3 sections in chapter 2. We'll definitely get one of them done. We may get 2, for like we'll get 3 done. They're pretty straightforward. This chapter has to do with logic and the proof of logic statements, truth statements, truth tables, and things like that. So we'll get to see the origins of math. The objective of this section is to discuss quantifiers and their effects on statements, talk about different forms of statements, how to determine whether 2 statements are logically equivalent, how to develop logical arguments, and how to determine whether an argument is valid. They use the word statements, arguments, equivalent. What does all that stuff mean? What is a statement?
Something that is true.
How do you mean?
Like a sentence that can.
You just read what's on the board. But what do you mean by true?
Oh.
What do you mean by true? Isn't cats are green a statement in English?
Like
No, that's it. We're now in the realm of yes or no. They're true or false. True or false. I mean, you can't get any basic than that. So it could be.
I guess it's false.
Why?
This cat's not green.
Are you sure there's no green cat anywhere?
No, that are alive. Is this supported by evidence?
What if I color one green? Isn't that a green cat?
Alive.
Sure it is. If I color his hair, women color their hair all the time. Why can't I color a cat's hair?
Oh, you mean like a real cat?
Yes.
It's not like biologically green.
I didn't say biological. I said a green cat. Well, no, this, yes. So when we talk about statements in logic, we talk about statements that can be determined whether they're true or false, which gets to validity, and which then takes us to arguments. So that's where we get to. Logic is used in mathematics thinking and reasoning and sense making. Statements can be either true or false, but not both. Statement represents in lowercase, and we'll write these things. Whenever you see a lowercase letter and an equal sign, that is describing or defining a statement. So for this example, P represents the statement, today is Monday. S represents the statement, it is raining today. T represents the statement, I am a student. Each of these are statements because they can be determined whether they're true or false. It's either Monday today or it's not Monday today. Example. The following expressions are not statements. Why? She has blue eyes. Why is that one not a statement?
It's not like a complete sentence.
It is. She has blue eyes. That's a complete sentence. Who's the she you're talking about?
We don't know.
No, it's too ambiguous. That's why it can't be determined as true or false. Because one person could say, if I say she has, one person's looking at one person, the person, somebody else, so it's not definitive. X plus 7 equals 18. That's not a statement. Good morning. Why is that not a statement? We don't know what X is. X is by definition a variable. It could be anything we want it to be. 2y plus 7 is greater than 1. We don't know why it's unknown. 2 plus 3. We don't know if it's true or false or anything. It's just that's not even a statement. It's just an utterance. 2 plus 3. How are you? How is that not a statement? Well, no, it can be true or false. No, exactly, because it's a question. Statements cannot be questions because questions have the answers depending on the person answering. So, yeah, that's exactly why, because it's a question. Very good. Try to trick y'all. Look out.
It's not true or false.
It's not a true or false, and it's an exclamation. So statements have to be sentences. Lincoln was the best president. It's very good. That's exactly what it is. The first three could be made into statements. How?
Variables.
Well, we define the variable for X and Y, yes. How about that she has blue eyes?
Putting like a person.
Well, yeah, I said that, in other words, if we were talking, you said she has, but if I'm pointing somebody, I'm defining somebody with that, with pointing them. So that's how we do that. Very good. Very good. And this is the explanation of all that. Yes. If a statement is true, oh, we're talking about negations. A negation. What does it mean to negate something? You ever heard that word negate? It makes something negative. In other words, it's to change the meaning of the statement. A negation changes it from true to false. If I said today is Monday, what's the negation?
It's not really-
Today is not Monday. Exactly. Very good. So the word not represents negation. So from a given statement P, it is possible to create negation of P, but this little tilde, this little symbol there, that tilde represents the negation of the opposite, the negative, which means not P. If a statement is true, its negation is false. If a statement is false, its negation is true. It just changes the truth value of it. We'll be doing a bunch of those today. Consider the statement, the snow is falling. The negation of the statement is what? The snow is not falling. That's straight up how it is. So that's a negation. And how is it represented in sets? It's the little tilde, little squiggle line. Because we use negations already in mathematics. What do we use in mathematics? What's the negation of 7? -7, yeah. So there's an example in mathematics. Just because it's changing the value of it. If I say 7 is true, then what's -7? It's not true. Here's examples. Negate each of the following statements. 2 + 3 = 5. What's the negation of it?
2 + 3 is 9.
Exactly. 2 + 3 does not equal 5. How do you represent not equal to in mathematics? The slash to the equal sign. Very good. A hexagon has 6 sides. What's the negation of that statement? Yeah, a hexagon does not have 6 sides. That's what it means. Does not have 6 sides. There's a negation of it. At a given time, the statements such as the shirt I have on is blue and the shirt I have on is green are statements. The reason they're statements is because they could be true or false, depending on, am I wearing a blue shirt? No. Can I wear a blue shirt tomorrow? Possibly, but that's tomorrow. So they can be statements. Otherwise than that, they can be non-statements because you can't prove it. Yeah, they're not negations of each other. I have a blue shirt on and I have a green shirt on are not negations of each other. Why?
Because they're saying 2 different things.
Yeah, they're comparing 2 different things. It does, just because I'm not wearing a blue shirt doesn't mean I can't have on a green shirt. So they're not negations of it. They're just a statement. Its negation has to be true or false, has to be opposites of each other. Yes, so if I have a shirt on that's red, then it could be a negation of it. Quantifiers. Quantifiers simply means to put a value, a number of things. That's what, when you quantify something, you make it a number. Some statements involve quantifiers and are more complicated to negate. A quantifier is given by how many of stuff right in the statement. So which words define how many? Well, we have three types, basically. We have universal quantifiers. By universal quantifiers, we mean all or none. Either all the students are in school today or none of the students here. Those are the universal quantifiers. They comprise of all of the elements in that set. Existential quantifiers. Examples are some, there exists at least one. Because if I say there exists at least one, what does that mean? How many can I talk about? One and up. One to all of them. So those are existential quantifiers. And remember, universal are everything, either everything or nothing. Think about this. The reason they call it universal is think of the universe. What's inside the universe? Everything. And then you can look at the other side of this. What else is in the universe? Nothing, because it's all empty, dead space. All, every, and each all have the same mathematical meaning. They're the entire set. And some, and there exists at least one, have the same meaning. If I say some, what does that mean? Or more. I mean, if I say some, that could be all just short of all of them, or it could be a couple. So it's just pretty much the at least one or some pretty much mean the same thing. It's not all or it's not none. And they have symbols. We have symbols for all those too. Assume the following is true. Some professors at Mountain View have blue eyes. Is that a statement? Yeah. This means at least one professor at Mountain View has blue eyes. Because yeah, if you were to prove that statement, some professors have it. You'd walk around till you see one, maybe two, maybe three, and you say, yeah, that's true. As long as one person doesn't and one person does, there's some. It does not rule out the possibility of all of the Mountain View professors having blue eyes, or that some of the Mountain View professors. Because if some do have blue eyes, what does that also mean? Some don't. So there, and we'll talk about those sets later on. If we look at some that do and some that don't, if you put them together, you have all the faculty. And that's a very important concept, which defines the universe. We'll talk about it later in this chapter. Because the negation of a true statement is false. Because the negation of a true statement is false, neither some professors at Mountain View do not have blue eyes, nor all professors at Mountain View have blue eyes, is the negation of the original statement. Why? Remember, the original statement is some professors at Mountain View have blue eyes. We're going to negate that. Some professors at Mountain View do not have blue eyes. Why is that not a negation?
That's what the first statement is saying.
Yeah, Bruce, they're saying the same thing, yeah, because you're not telling me that it's not negating, yes, that's true, they are. What would be the negation of some? All or none, yeah. So, yeah, so that's very important when we look at there. One possible negation of the original statement is no professors at Mountain View have blue eyes. Well, no, we can't use all because some could mean anything two or all of them or more. That's some. Here are the negations of these statements. The opposite of some is no. Some are not. What's the negation of that statement? All, yeah. The opposite of all is some. Why is that? Why is the opposite of all some? Yeah, because if you're saying all of them, all you do is prove that one of them is not there, which is some. The opposite of no is also some. In other words, you see how the universal quantifiers, the opposite of a universal quantifier is an existential quantifier. Actually, and we'll see later on, these words all have different symbolic meanings. All right. Examples, negate each of the following. All students like hamburgers. What's the negation of that? Some students like hamburgers. Some people like mathematics. Okay. Some students like mathematics. No students like mathematics. There exists a natural number n such that 3n equals 6. Or there does not exist a number n. For all natural numbers n, 3n equals 3n. Or we actually, I don't see why we couldn't say that 3n does not equal 6. So I think we can say that too, because that would mean the same thing. For all natural numbers n, 3n equals 3n. What's opposite of all? Yeah. For some natural numbers n, 3n equals or does not equal 3n. Some prime numbers are not odd numbers. So here, look up here where we had it. Are not. Some are not. The opposite of that is, yeah, so all prime numbers are odd numbers. Yeah, we can make the negation there. Now comes the fun stuff. Truth tables. It all started with puzzles. For example, by this guy, Smulian. Each room has a sign on the door. And the prisoner knows that exactly one of the signs is true. The signs are, in this room, there is a lady, and in the other room, there's a tiger. That's in room 1. Room 2, in one of these rooms, there is a lady, and in one of these rooms, there's a tiger. With the information on the signs, the prisoner can choose the correct room. Which room would you pick? Who picked 1? Why?
Because it's in this room. There's a lady and another. I would not take the choices.
Now, is that a true statement, though? Because in this one, if the first statement is true, the second one's true. But if it's false, the second one's false.
Right.
But the second one, in one of these rooms, there's lady known, they're both true. So you can't go wrong with the second one. They're both true. Is there a lady in one of the rooms? Is there a tiger in one of the rooms? So the safe door to take is the second door. Because on the first one, you have a 50-50 chance. Is it true or is it false? Remember, these are statements. Can you prove there's a tiger in the room? Open the door and find out. Yeah, see, the scenario cannot happen because it could be true or false, and we can't detect which one's which. But the second one, it's always true. So the second door is the right one. Truth tables. Now we get to the fun stuff. When we create truth tables, each element, by element, remember, what does P represent? A statement. So we take whatever statements we have and we look at their possible true or false statements and whatever else it says in there. So the statement, if the P is true, the negation of P is false. If P is false, the negation of P is true. So you see how it just changes the sign of it. Compound statements. In English, we talk about compound statements when you join two sentences. This and that. Those are compound statements. They have either conjunctions or disjunctions. You remember hearing that in English class? So a conjunction is that brings two statements together. The conjuncting word is and. Today is Monday and it's raining outside. That's a conjunction. And then the other statement is the disjunction. It's raining outside or it's Monday. Now, each one of those have a truth table, which we're going to look at in a second. Because we are using symbols here, whenever you use the and operation, it's we call it upward caret. That stands for, that little symbol there starts for and. The downward, the V, stands for or. So if you have and, use the up arrow, up key, caret, and then down is a V, is the or. Let's look at this. P represents snow is falling and Q represents the ski run is open. The compound statement, the snow is falling and the ski run is open, is represented by P and Q. Because you took each of these statements. This is what P was equal to, and this is what Q is equal to. So we denote those. Because once we take the statements, these big long, because it would be horrible having to write this over and over. So we allocate it to a letter, a lowercase letter, and then we use the symbols for and or. So similarly, if I use the or statement, then in between P and Q, it's a down arrow, the V. Yes. Actually, the next part I'm going to show you is so we have the and operation. That one is it up or down? Then we have the or, which is the V. We have two statements, P and Q, or P or Q. We can create truth tables for both of these. Okay, now since I'm creating truth table, when you create a truth table, you have to first start off with the letters you have in your statements. So I have P is here, and I have Q. And I'm trying to find this statement. So P and Q. So they could both be true. The first one could be true, the second one could be false. The first one could be false, the second one could be true. Or they could both be false. We have to look at all possibilities. Right, so true and true. How do we, well, let's also set up the other one while we're here. It's P, Q, P, or Q. How do I know there's supposed to be 4 rows? Well, yeah, but what if I had 3? What if I had P, Q, R? How many rows do I need there? Nah. The number of letters that you have, we'll call that N. So we have 2 letters, P and Q. So in this case, N equals 2. The number of rows needed equals 2 to the power N. The reason it's 2 to the power N because we only have 2 possible outcomes. It's either true or false. And it happens with 3 numbers or 2 numbers. So since N equals 2, 2 to the power 2 equals 4. That's how many rows we need. So if we had 3 letters, we need to have 2, 4, 8 rows. All right, so far so good. The and statement. The and statement, if look at a pipe. If you have a pipe and we have two valves in here, this is valve P and this is valve Q. If they're closed, that equals false. If they're open, that equals true. Okay with that? So if I poured some water in here, let's look at this. If it's true, what do you mean by the doors here? Are they open or closed? If they're both open, what will happen to the water? Will it come out? Yeah. So if it comes out, it's true. And if it does not come out, it's false. So in our first table, true and true. So both doors are open. If I pour water, will water come out? Yes. In the second one, the first one's open, the second one's closed. Will water come out? No, so it's false. If the first one's closed and the second one's open, no water comes out. Or if they're both closed. So that's the truth table for the and statement. Why did I draw a pipe like this? Because both the first door and the second one work together. They both have to operate at the same time. On the or statement, this is the or statement. This is P and this is Q, same thing. If it's open, it's true. If it's closed, it's false. If it comes out, it's true. If it does not, it's false. So let's do our truth table. We have true, 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 false, false, true, false, false. Go ahead and draw, because remember, now we can put water in both of these pipes. Fill in the blanks here. What's the first one telling me? Well, if I put water in here and both gates are open, will water come out? Yeah, so that's true. If the first gate's open, the second one's closed, will water come out? Yeah. If the first gate's closed, the second one's open? Yes. If they're both closed, will water come out? There's the easiest way to memorize those. Because now in this part of this section, we're gonna be doing truth tables with all sorts of symbols. Yeah. There it goes. Truth tables, compounds. So here we have the and statement. True, false, false, false. And the or, which is a disjunction. And here's its, we just did those. All right, let's look at these. Let P be 2 plus 3 equals 5. Let Q be 2 times 3 equals 6. And let R be 5 plus 3 equals 9. Classify each of the following statements as true or false. Okay, well, what we have to do first is what? Well, when we don't know, we have the tables already. We did those on our sheet. But what we have to do first is determine if P, Q, and R, if those are true or false statements. Is P a true statement? So P is true. So we know that P is true. What do we know about Q? It's also true. And R is false. So in the first one, P and Q, true and true equals what? True, very good. How about B? You're asking me. What is Q? True or false? And R? Was that true or false is true. So here we have not P. So what is not P? No. We're looking at true or false only.
Oh,
Not P. P is true, so not P is false. False and R is false. So false and false is false. So it's false. So it's true, true, false. Okay, do the last three. What is not P? False, not Q. So this statement would be false, or false would be false. They're both closed, so nothing comes out. Now, notice the negations on the outside of the parentheses. Remember, in mathematics, order of operations, what do you do first in a math equation? Parentheses. This is where it came from. It came from logic. We do inside the parentheses first. So we have P and Q. What is P and Q? True. So not true would be false. Very good. P and Q. So it's true and true is, or what is not R? Now, if R is false, so if I negate it, it becomes true. So it's true or true, so this statement is true. So those are all the answers. The way you would do these, whoops, would be by creating truth tables for each one of these. In the first one, we have P, then Q, and then so we have P is stated as true, Q is true, so P and Q is true. That's it. You do it for each one of those. And that's how you'd solve it out. And that's what this tells you. Make a truth table for this. So I create a truth table at P, one column for P, not P, and then the entire statement P or not P. Since we only have one letter, that means we only need two rows. 2 to the power 1 is 2. P is true, not P is false. If P is false, not P is true. True or false is true, false or true is true. A statement that's always true is called a tautology. A statement that's always true is tautology. Truth tables are used not only to summarize truth values of compound statements, but to determine whether two statements are logically equivalent. Logically equivalent. Two statements are logically equivalent if and only if they have the same truth values in every possible situation. So two statements are logically equivalent if their truth tables are identical, if the conclusions are the same. So if they're logically equivalent, we use the triple equal sign. That means no ifs, ands, or buts, they're equal. So again, two statements are logically equivalent if they have the same truth table solutions. Example. We'll talk about De Morgan's laws in a second and how they relate to our mathematics. How many rows do we need?
4.
Very good. We need 4 because there's only 2 letters. How many columns do we need? Well, let's see. You need to have one for P. You have to have one for Q. You have to have one for this statement, P and Q. You have to have another one for not P and Q. You have to have one for not P. You have to have one for not Q, and you have to have one for not PQ, and then you have to have one. So you see how it builds up. So we're going to need a whole bunch of columns. Let's see. So we have P and Q. Then we have to find P and Q. Then we have to find not P and Q. So that's in the first statement. Then we have to find, since we already have P, we have to find not P. We have Q, we have to find not Q. Then we have to find this entire statement. And then we have to find the entire statement. So we need four rows, because we have true, 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 false, false, true, false, false. So true and true is true. True and false, false. False and true, false. False and false, false. Very good. So in the fourth column, what do we do with the, what do I do now? Yeah, we negate the column we just did. Then we change this, we just change all of the elements. Since that's true, it becomes false. Since that one's false, it becomes true. This one becomes true, and that one becomes true. So there is our left side. You follow me so far? Now let's do the not P and not Q. So not P would be what? Here's P. So not P would be false. So this one's, next one down there is true, so it becomes false. The next two are true, so they're are false, so they become true. Q is TF, TF, so it's FT, FT. So to find these, I go to the first two columns. That's where P and Q are. I negate them. Okay, not P or not Q. So false or false is false. False or true? True or false? True and true. So here's our other side. Now, are they equal? Because are they logically equivalent? Look at this one, false and false. That's true. True and true. That's true. True. Are they equal? Yes. Are the last ones equal? Yes. So De Morgan's law is, notice they're all true. So that means De Morgan's law is a what? It's a tautology. Since all of the values of the solution are true, then this is a tautology. Now, have you all seen that? You've all have seen this before in mathematics. In mathematics, we have the distributive property. Distributive property. The distributive property is this. A times x plus y equals what? I take the letter in front and multiply it to everything inside there. So in essence, the De Morgan's law just proved this. Distributive property in mathematics. If I have that, what's this equal? If I had 3 times x plus 5 plus 3 times 5, which is 3x plus 15. That's distributivity. So that's what this is saying. That's what De Morgan's law is saying. What De Morgan's law is saying is, where's my squiggle? So if you distribute this negative to everything inside there, what do you get? You get negative p, negative arrow up, and negative q. So this goes to everything inside there. So far, so good. So we have no p. What's the negation of an and? Or. So it becomes an or. So that's what the De Morgan's law proves to us. If you negate an and statement, it becomes an or statement. which is exactly what the distributive property. This distributive property took a multiplication equation and made it into an addition equation. Can we go backwards? Yeah, because in order to be equal, I have to be able to go from this to this. So yes, both directions have to be true. It's a tautology. And did we mess up one? No, because that is true. And that's false. False or false is false. They're both equal. Why? Oh, that, yeah. This is, if this is false, then that's false. This is true, that's true, that's true, that's true. So they're both equal. They just left off the last column. And here's De Morgan's laws. If you negate an and statement, you get an or statement. If you negate an or statement, you get an and statement. Okay. All right. Conditionals and biconditionals. A conditional or an implication is an if-then statement. The reason is, okay, conditional. Growing up in your house, how many times have you heard, if you clean your room, you can go outside? Or your brother, you're sitting on your face, says, if you smell my fart, I'll let you go. Yeah, that's a condition. So those are conditional statements. Those are if then. If you do this, then this happens. And instead of the if then, it's implied. So that's where we use an arrow. P implies Q, or if P, then Q. Everybody know what the word implies mean? It leads to the conclusion of. So whenever you see an if-then statement and it's in words, you can just put, instead of that, just put the first statement, arrow the second statement. All equilateral triangles have acute angles. If a triangle is equilateral, then it has acute angles. That's an if-then statement. It says all equilateral triangles have acute. So if you have an equilateral triangle, then you have to have acute triangles. So this would be P arrow Q. Hypothesis. This is what you're claiming. That's the if. If this is true, then the conclusion happens. An implication may also be thought of as a promise. If you do this, I'll do this. Suppose Betty makes a promise. If I get a raise, then I'll take you out, take you to dinner. If Betty keeps her promise, the implication is true. If Betty breaks her promise, the implication is false. So we have these possibilities. Remember the two statements. If I get a raise, that's P. I will take you to dinner is Q. So if P is true and Q is true, she gets the raise and she takes her dinner, promise is kept. True, false. She got the raise and she didn't take you to dinner. That's false. Did not take you to dinner. She broke her promise. False, true. If I don't get the raise, then it doesn't matter what happens. Because the statement only if I get the raise, I get you dinner. If I don't get the raise, it doesn't matter. I don't have to take you dinner or anything. So if the first one's false, I don't get the raise, then I'll take you to dinner. It's true because it doesn't matter. If the first one's false, it doesn't matter what the second one is. Now, let me show you how. Remember how we did the diagrams earlier? For an if statement. If P, then Q. Or P implies Q. If P happens, then Q is going to happen. So let's look at the truth table. How many rows? 4 rows. So we have P here. We have Q. Then we have if P, then Q. So true, 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 false, false, true, false, false. The easiest way to think of this one . Here's an if then. Think of business. Think of business. Up here is true. Down here is false. Because if you make money, that's pretty high up there. If you lose money, you go down here, you're bankrupt. So far, so good? So if you go from true to true, you didn't make any money. Is that bad or good? You didn't lose any money. So if you broke even, that's good. True and false. If I started up here, ended down here, I lost money. Is that good or bad? That's bad, so it's false. If I started down here and made money, is that good or bad? That's good. Or if I stayed down here, I didn't go anywhere, so breaking even is good. So the only time we lose anything is when we lose from true to false. If we go down the cliff. I'm thinking we're walking across, we don't lose anything, we jumped across. Here we fell. This one we're climbing. So the only one that's bad is from true to false. And that's the truth table for the if then statement.
It goes from false to true.
What's that?
This is the only time it's bad, is if it's
No, if it goes from true, because true, you have money,
true to false.
and then false, you lose money. So there's our truth table. True, false, true, true. Trust me, the diagrams I showed you, if you remember those, it makes it, you won't mess them up, because the other way of doing it is just memorizing them. And that's a lot of extra work. If you put it to a picture, it makes it a lot easier. An implication, remember, it's an if then, can be worded in several equivalent ways. If the sun is shining, then the swimming pool is open. If P, then Q. If the sun is shining, the swimming pool is open. If PQ. If the swimming pool is open, that the swimming pool is open if the sun is shining. Q if P. These are all the same thing. It's just they're stated differently. The sun is shining implies the swimming pool is open. That's if then. P implies Q. The sun is shining only if the pool is open. The sun is shining. The sun shining. Okay, so the sun shining is a sufficient condition for the swimming pool to be open. Sufficient condition. What does that mean? It's enough to. If the sun is shining, pool is open. The swimming pool being open is a necessary condition for the pool for the sun to shine. So if the pool's open, then the sun's shining. Or since the pool's open, the sun must be shining. So all of these mean the same thing. They're just worded differently. So you see how you have to be very careful how you read these things. Now let's look at the three possible. Here's our statement. Converse. The converse is you flop P and Q, flip them. The converse of the statement, if P then Q, is if Q then P. That's the converse. The inverse is you negate the statement. So if P then Q becomes not P, then not Q. And a contrapositive is you flip them and you negate them. So you negate the converse. Ooh, wow. It's already time to go. So that's the conditional statement, and it's the way you could take P and Q and flip them around and negate them. There's also another one called a biconditional one. Let me get to. Well, here, write the converse, inverse, and contrapositive of this one. If I am in San Francisco, then I'm in California. What's the converse? If I'm in California, then I'm in San Francisco. What's the inverse? If I'm not in San Francisco, then I'm not in California. And the contrapositive, beautiful, excellent. And there's all of those. I trust you all know how to do that. Well, yes, as it says, the implication P then Q and its contrapositive are logically equivalent. What does that mean if they're logically equivalent? They have the same truth table. Yeah, well, no, exactly. The tautology has true in all the ends, but with these two will have the same truth values. So if this one's true, that one's going to be true. If this one's false, that one's going to be false. So they have the same outcomes. Yeah, we don't have time for that. Well, here it is. Ooh, good. So here's the first one. If P then Q, true, false, true, true. If not Q, then not P. True, false, true, true. Since they have the same outcomes, they're logically equivalent. Now I'll put this on. Oh, here it is. Biconditional. Biconditional has to be true both directions. For biconditional, it has to be true both directions. And that's where we use the word if and only if. If you see the words if and only if, then it's the arrows pointing both directions. So P, if and only if Q means that if P, then Q has to be true, and then if Q, then P has to be true. So they have to be able to go both directions. We'll talk about the Venn diagrams next time. Yeah, we'll talk. And that's the last part of this section. This section is the Venn diagrams. All right, so that's it for today.